Assalamu alaikum. So today we'll discuss the case two for reverse curve. So we did one case in which the two lines were non-parallel, and now we'll do a case in which the two lines are parallel. And there are numerous ways to solve this. You can apply the rules of simple circular curve. You can apply the relationships that have been developed before. But in this case, we will develop some other relations which are applicable to only this case in which it's a reverse curve and the two lines are parallel. So if those conditions are there, then a few other equations that you can apply, and they can help you to lay out the curve in other ways. So let's say if you don't have if you don't want to use a theodolite, so by using these new relationships or new values, you can lay out the curve, you can determine the center point of the curves, and so on. So let's see what is different when the two lines are parallel. So over here we have two lines, PQ and RS, which are parallel and which are y distance apart. And it is required to join the two lines with a reverse curve having equal radius. So that's another condition over here, that the two curves have equal radius. We can also do it for non-equal radius as well. The difference is that the center point or the ending point of the first curve and starting point of the second curve won't be at a distance y by 2, right? Won't be at the midpoint. But that's the other case. We're doing a very simple case in which the two radius are equal, and that's why the center point lies at exactly y by 2. So r is the common radius, and c is the point of reverse curve, the point at which the first curve ends and the second curve starts in the opposite direction. T1 and T2 are the tangent points. Phi, like before, is the deflection angle, and T1, T2, the length, which is the length of the line joining the points T1 and T2, and X is the perpendicular distance between T1 and T2, and Y is the perpendicular distance between the lines PQ and RS. So we have X distance, which is basically the distance between the starting point of the first curve and the ending point of the second curve. So it's a horizontal distance. It's not along the curve. It is if you draw two lines which are perpendicular to the line RS and the line PQ, starting at the point T1 and T2. So that distance would be X, and Y distance is perpendicular to the two lines, and we've discussed this before. So for this curve, we have the data that needs to be calculated. First, the long chord of the first curve, so which is equal to 2r sine phi by 2, which is the distance between T1 and the point C. And similarly, we have the long chord for the second curve, which is again 2r sine phi by 2. Now the length, uh, which is the sum of the two chord lengths, the length T1, T2, is equal to 4r sine phi by 2. And that is because since for both the curves, the angle of deflection is equal and the radius is equal, so you get a very simple relation. Now, another relation that we can derive is from the triangle T1, T2K. So we have this triangle T1, T2, which are the points which are shown, and then this point over here is the point K. And in this triangle, uh, we can use the relation of sine. So sine phi by 2, and this angle, remember, is phi by 2. And this is basically the same thing that we have done before in a simple circular curve in which you have the two tangents and this is a long chord and this angle is equal to phi by 2. And that is why when you lay out the curve by deflection angle method, the sum of the angles or the end deflection angle is equal to phi by 2. So over here, if you apply the relation for sine, so sine phi by 2, so that would be equal to this value y over here perpendicular divided by hypotenuse, which is equal to L. And if you replace the value of sine phi by 2 in the equation above, which is the length T1, T2 is equal to 4r sine phi by 2, so you get an equation which is equal to L is equal to 4ry over L, or L square is equal to 4ry, or the length of the two long chords added is equal to under root for the radius of the curve and y, which is the vertical distance. So from here, if you know the radius, if you know the length of the long chords, we can calculate the perpendicular distance between the two parallel lines, which is equal to y. Alternatively, what we can do is that we can calculate the distances T1a and T2b. So T1a and the T2b, which is as of now half distance. But if you want to calculate it in some other way, if let's say the two radius are not equal, then obviously you can't use the above relation that we have used, because that uses the common radius and the common angle of deflection. So if that's not the case, then you can apply this other equation of finding out those distances. So T1a is equal to O1T1 minus O1a. So T1a is equal to O1T1 minus the distance O1a. So we have to find out a relation by which we can find out these distances. So for O1T1, it is equal to radius. So it is evident from the figure that every line which joins the center point of the curve and any point on the curve is basically the radius. And then the other one we had was O1a, which is equal to r cos phi. So this distance O1a, uh, yeah, this distance O1a is equal to r cos phi. And basically, how do we get that? The interior angle is equal to phi, like before. One of the side of this triangle is the radius. So by using the known side and known angle, we can calculate the distance O1a. And basically, what we want to find is the distance T1a, and we have used the known values. So O1T1, which is equal to radius, and then from that we want to subtract O1a, for which we can use the relation of phi, and basically this is how we can get the distance. And similarly, for the other side, we can do the same thing on the other side for the other simple circular curve in order to calculate T2b. So it's basically the same thing, and we get the relation at the end, which is r into 1 minus cos of phi. So if you want to calculate y through this method, so we used one method before, but if you want to use this method, so we can add the two values and we can get y in that way. And in order to calculate x, which is the perpendicular distance to y, uh, we can use, yeah, we can use the distances AC and BC, and again, we can use the same triangle that we used before we use the condition of cos, and now we can use the condition of sine using the same triangles, and we can get the x distance. So basically, what we have done is that we have developed a few more relations which are based on geometry, because since the two lines were parallel, so we could use geometry and different relations to determine some relations which can be used in specific case in which the radius is same, phi is same, and the two lines are parallel. And we have used a method which we can apply to another case in which the two radius might not be equal. So now that we've done this, we can quickly glance over the related problem. So in this question, we have a reverse curve which is to be set out to connect two parallel railway lines 30 meters apart. So since they have given you that the two lines are 30 meters apart, so that becomes your distance y. The distance between the tangent points is 150 meters. So they have given you the distance T1, T2, which is equal to 150 meters. Both the arcs have the same radius. So that means the deflection angle is also the same. And that means that you can use all the relations that we have determined earlier. The curve is to be set up by method of ordinates from the long chord. Again, that's not the method that we are using. We're using the method of deflection angles. But then again, this ordinate method from long chord is very basic, and it can be applied if you don't have a theodolite to work with. So in this question, what they have given is that T1, T2, distance is equal to 150 meters. And then we can use the relation for finding out T1, T2, which is 4r sine phi by 2. And from this relation, since we weren't given the radius and we weren't given phi as well, so we can develop this relation. Now, radius is still unknown, but we can use a relation to determine this value of sine phi by 2. And for that, what they have used is they have made use of the different lengths that are given to us. So remember how we did use a triangle T1, T2K. So again, they've used the same triangle T1, T2, K, and K is not shown, so we can write it down over here. So this point would be K. And if you apply the sine relation over here, so what we have is we have sine phi by 2 for this triangle over here. So we have perpendicular, which is 30, and we have hypotenuse, which is again given to you, which is 150. So you can basically either find out the value of pi, or you can replace the whole thing in the equation given below. So we can replace it and we can find out the radius, and then again we can find out phi as well. So this is what you need to know, radius and phi. Now that you have those values, we can apply the method of deflection to find out the deflection angles. And in order to do that, you can start from either sides, from T1 or T2. The calculations would be the same, everything would be the same. And you just have to find the reflection angles once, and you can apply it to other side as well. So this is all about the reverse curves, and I'll see you in the next lecture. Thank you.